All right, thank you very much. I hope I can live up to those expectations. I think I have something pretty good in store for you today. So yeah, thrilled to be talking to you today about summoning Boolean circuits. My name is Andrew Morris, and I work for the Ethereum Foundation. So this work is actually funded by them. But I won't actually be talking about Ethereum very much today. So if you want to use this technology, you don't have to use that part of it if you don't want to. But if you are interested in that, it is something that we are going to be linking these things together so that you can connect them together and do fun stuff with both things. But yeah, with that out of the way, let's get into it. So part one, I want to talk about what this thing is called MPC. So I have some good news. I have another story for you guys. Some of you may remember last time I explained MPC with a story. I think that went pretty well, so I'm doing that again. It's a different story, so don't worry. Hopefully you'll get some value out of this one, even if you saw the previous one. So to kick things off, hopefully this makes you feel a little bit uncomfortable. That's kind of the point. So money is taboo. The reason why this kind of interaction doesn't really happen is because we're afraid of this kind of interaction happening. And so instead, you might find your conversations look a little bit more like this. So you may be thinking about money or other things that are more consequential to you, but it's human nature. It makes sense. Things are taboo for a reason, and so you might find yourself talking about the weather a little bit more than you would like to. So, but think about what you're missing out on. If you could see everyone's pay, if you could see all the money, this would be a superpower. Does the pay stink where you work? Or maybe it's just you. Does that mean, should you ask for a raise or should you look for a job elsewhere? Or maybe you could find out that actually you're paid pretty well, and it would be nice to find that out as well. But the point is that we don't know this because, too bad, crystal balls don't exist. So we have to communicate with each other instead. And a little bit of practical advice. Oh, sorry, this is, we still have this taboo problem, right? So a little bit of practical advice if you feel that you might be in this situation where you want to talk about money. You should really consider braving the taboo. I think there's a lot of value to be gained in doing that. And I think a lot of people, I feel myself, I am guilty of this, don't talk about money enough. And there's a lot of value to be gained in there. However, I want to offer another interesting alternative that might be a little bit easier. So if we think about this problem, you think about, you might not actually need to know what the exact dollar amount that your friend earns. But what is really important to you, what is most of the value you would get out of learning that information is, if this person that they work a similar job to you, most of the value in learning their exact number would just come in the form of do they earn a similar amount to you or not? Or is there a difference here that's worth caring about? And so the question, this mathematical puzzle is, can we learn this information without sharing this number with anybody? And I think it's unnatural to ask this question because it seems like a silly question. How could you possibly calculate on something that you can't see? Very, very strange. But this is the whole point of MPC. You might not think to ask this question, but this is totally what MPC allows you to do. Basically, it allows us to analyze data without looking at it, which is nuts, right? How can you analyze data that you can't see? But I promise you that it's real. We can totally do this. And so I'm going to be explaining that tonight. So I'm going to be showing you how you can leverage this technology for yourself. It's all open source, and you can ask me for help if you get stuck as well. I really want you guys to succeed if you decide to try this out. But for this particular problem, I have this application for doing this specific thing. It's called Ballpark. Very simple. Start, host a session. You get to choose what about the same means, because there's not much point finding out that your friend owns $1,000 a year more than you. That will make you just feel awkward for no reason. So it'd be better to just find out that it's about the same. And also, if you find out that somebody earns more, you really want to make sure that that is a significant amount more. So that's what this allows you to do. So you can configure what you feel that should mean. So we have this default of 15%. Curious what people think. But anyway, you can change that if you like. You get a joining code, get somebody else to just scan that, they join, then you're linked together. You both enter your compensation, click calculate, and then you can get this result out. Simple as that. There's no ads, there's no signups, there's no installs, and very importantly, there's no computer in the middle that did this calculation and just pinky promised to do the right thing. We're solving this problem with math, not with trust. So back in our story, if our characters use this technique, they can get this kind of result instead, which is much better than that first slide. You know, your ego may still be bruised by finding out that you earn less, but if that's all of the information that you learn, then hopefully there's a lower chance that you're going to fly off the handle and be outraged and forget that, hey, the practical consequence of this is, hey, maybe you should ask for a raise if you find somebody doing similar work that is earning more than you. So Ballpark is a real app. I don't have very long to say on this slide if you want to capture it, but there will be a link to our website later and you'll be able to find it pretty easily from there. All right, so part two, how do we actually make this work? So I made this language called Summon. And what does Summon do? Summon bridges this gap for us because the flavor of MPC that we have available relies on you defining a Boolean circuit. So I've been saying that, you know, MPC allows you to analyze data without looking at it. And that analysis has to be represented somehow. And it turns out, yeah, the way that we need to represent that analysis is with a Boolean circuit. And that's pretty inaccessible if you want to just try to write, you know, and or gates and things like that by hand. That's not a very practical solution. So I created Summon to bridge this gap. So you can just write TypeScript and you can generate these Boolean circuits, which is pretty cool. And so hopefully the idea is that can connect everybody to this magical MPC technology. So this is the Summon program for generating the circuit that's used by Ballpark. We start off by taking this public input called tolerance%. And it's important to distinguish between public inputs and private inputs. Public inputs are much easier to deal with because the compiler doesn't actually need to emit any circuitry associated with doing calculations on inputs that like everybody can just see, because if everybody can see it, then you can just do the calculation. There's no need to use this special cryptography, which is a lot slower. It's practical, but it's a lot slower than running calculations normally. So next up, we take these inputs, private inputs from party 0, party 1, what their compensation is. So that's coming from that screen. And then we output a result, which is the result of calling this compare function. So let's get into how that function works. So the first thing it does is it applies this cap of 1 trillion, which is hopefully enough to cover people's compensation. It is actually disclosed on the app, so just in case you're doing something funny, you can see that's happening. You don't get into an awkward situation. It's like, sorry, the app won't let me put in and that reveals the whole thing. So hopefully it doesn't happen. But even if you're in, dealing with millions of dollars, you just say, hey, we're going to deal in millions of dollars instead of regular dollars if you're valuing companies or using it for some other use case. Anyway, so this is the rest of the file. This is, there's not very much that you need to do in order to find something like this. So I'll just go through it line by line. Firstly, we just compare the two compensations to figure out, whether they're in order or not. Remember, this is happening inside of MPC, so even though we're calculating this, nobody can see it. Next, we use that flag. We use it to actually put those two numbers in order so we know what the small value is and what the large value is. This also showcases that we have these nice creature comforts of TypeScript and JavaScript that we've come to know and love. So here you can see ternaries being used and arrays and destructuring. All of that stuff works. You might expect, because this is like a re-implementation of JavaScript. This does not rely on any mainstream JavaScript engine or even any third party. Like this is a whole new thing. And by the way, in Summon, the length of an emoji is 4 because because Summon uses UTF-8 like God intended. Anyway, so next line. So this next line, I feel like this is kind of the heart of the program. This is detecting whether the difference is significant or not. And it might look a little bit strange. The reason for that is because in Summon, unfortunately, at the moment, we only have integer arithmetic. So floats are a lot more complicated to deal with. And so, but you'll find that you can actually get get away with integer arithmetic in a lot of cases. And so it's just a matter of like rearranging this inequality a little bit, and we can calculate this kind of thing without using floats, because we really want to know whether large divided by small is greater than 1.15, right? And so yeah, we don't have to do floats in order to achieve that. And so finally, we test these two flags to output our result. So 2 will signify that there is no significant difference. 1 if party 1 has the significantly higher compensation, and 0 if it's party 0. So to reiterate, sorry if I'm beating a dead horse here, but I think this is amazing. You know, this is the output that we get, and it actually depended on us finding out this, you know, are the two compensations in order? Who actually earns more? That was calculated in the middle, but nobody has access to that information. Even if you use a modified client, if you're doing this with somebody with modified software, it's impossible to extract this information. The only thing they can get out is the result. Cool. So once you've written your circuit, you can compile it like this, summon.compile. So summon is written in Rust, but we use WebAssembly, we use WASM bindgen. So you can access this from within your TypeScript application, which is really useful if you have like a dynamic circuit like this. Like if you select a different percentage, you actually generate a different circuit. So that means that we can't build the circuit ahead of time. And so you get this benefit, and it also just makes it a lot easier. You don't have to deal with this separate build tool. It's just all part of the same TypeScript project from end to end. So yeah, we specify the files, the public inputs, boolify width. So we have 48 bits of precision. That's to cover our 1 trillion maximum, which should be plenty, right? And then we get this output. Now, when you're making an MPC application, you don't need to worry about dealing with this output. You take this thing and you pass it to the next part of the API. But we're just looking at it because it's interesting and to understand the internals of what's going on. So we get some metadata about where the inputs and the outputs are. And then we also get literally the gates. So we get inversions, and we AND 2 gates together, and we XOR things and invert more things. And all of that adds up to the calculation that we want to do. Cool. So I'm going to zoom in on this expression. So it's the heart of it. So we're going to follow this expression through the compilation process to see how we get a Boolean circuit out of that. So the first step is using this thing called SWC. You might have heard of SWC because it's actually intended to be part of the JavaScript ecosystem to give you better build tools. It's an alternative to the TypeScript compiler, but it doesn't do any of the type checking, but it's really, really fast. And so in Summon, we use just the parser component of that. So we can literally get, it really is TypeScript syntax. There's no gaps, at least in the syntax level. And we get the data structure, the abstract syntax tree, so that we can then do compiling and fun stuff with it like that, take it in a different direction. So here are the next few steps. Once we parse it and we get the abstract syntax tree, we do this file by file, by the way. So you can have multiple files, you can have imports and exports and build complex projects if you like. And so for each file, we have an abstract syntax tree. Then we compile each of those individually to get assembly for every file, per file. We then link those together to form assembly that represents, one assembly that represents the complete program. There's also an optimizer step, which is really important. One of the actually really nice benefits of this is just that you get sensible looking assembly out. If you just compile something without this step, the compiler is really, really literal. So it generates all of these extra internal temporaries and things that you would never think of. And if you look through it carefully, it's like, oh yeah, there was this thing, you would have to do that. But our human brains will just kind of short circuit that. And if you write assembly by hand, not suggesting you should do this, but if you were working on compilers and you were writing assembly by hand, you'll write something like this. And the optimizer this optimizer is not very sophisticated actually, but one of the really nice things that it does is it produces this relatively sensible output for us that we can read. So then there's just a couple more steps. After we have this assembly, we pass that to an assembler so that we have a bytecode, and that gets fed into a virtual machine to basically run the program, and we get a circuit out of that. And I have this offshoot up here, this dotted arrow with a line through it for value script. So Summon is actually a fork of this other project that I did, value script, and which I did outside of my capacity working for the Ethereum Foundation. And so I saw this wonderful opportunity that like, hey, I could totally repurpose value scripts to make circuits, and it's way better than what we were doing before. And that's worked out really well. But yeah, value script is designed so that you can just sort of run regular programs. So if you're interested, and that's still accessible to you if you're interested in that. So if you're interested in that, yeah, feel free to ask me about that later. Anyway, so we're going to go through this example. Remember, this is the assembly which represents that core comparison that I've been talking about. So we're just going to go through this line by line and see how that generates a circuit. So we have this multiplication. So multiply large and 100 together to produce temporary 8. Then on this next line, we have an addition. So this is saying 100 multiplied by tolerance percent to produce temporary 9. And yep, that's that. But so tolerance, remember, is a public input, which means that at compile time, we know what this value is, which means that we don't actually need to generate circuitry for this. Instead, we can just substitute the value that we know for that in here. So we have 15, and the compiler can say, oh, temporary 9, that's just going to hold the value 115, which means that we don't need to include this node in our graph, and we can just say we have 115 instead. Next line, with multiplication, small times 115 multiplied together to give temporary number 10. Then we do a greater than operation of temporary 8, temporary 10 to produce this Boolean is significant. And then the next thing is we just get rid of these nodes in the middle here as just a convention. It makes it easier to read these graphs, join them together directly, and we get something that looks like that instead. Cool. So that's our circuit, kind of, but you might notice that this is not a Boolean circuit. This is an arithmetic circuit. The title of this talk is Summoning Boolean Circuits. So you need a Boolean circuit to do MPC. So how do we get from this arithmetic circuit to a Boolean circuit? So the answer to that is this other component called boolify. And so yeah, boolify will take this arithmetic circuit and produce literally and an XOR and inverse gates. You might be wondering where the OR gates are. We don't actually use OR gates because it turns out you don't need them. And there's complicated reasons why we choose not to represent them. But if you want to have an OR gate, you can represent it using a few AND and XOR gates. I forget exactly what the expression is, but anyway, it's a complete system of logic with just these three. So unfortunately, though, I made too many slides. So I'm actually going to be coming back next month. So if you're interested in seeing how arithmetic circuits can be... Sorry? Yeah, you're going to have to wait a whole month. I'm very sorry. You can look at the source code if you like. It's all open source, and you can get it that way. But yeah, I'm going to be coming back next month, and so you can learn all about how to boil this down into Boolean circuits next month. So yeah, please come back for that. Looking forward to seeing you then. This is not the end of the talk, though. So the other part is how MPC works. So you might be saying, hey, Andrew, this stuff is all really cool, but you keep harping on about this MPC thing and like it's the coolest thing since sliced bread. So, how does that part work, right? I'm sorry, but you're going to have to come back next You're going to have to come back next month if you want to learn about that. I'll be going through all how the underlying cryptography goodness works for that. Okay, I promise I won't bait you into another teaser. I just want to finish with this. So there's this other app. So Ballpark, I want to encourage you. Hopefully we have time. I'm not sure whether we'll have time to socialize and try this after this. But the Ballpark app, please do give that a go. But I imagine it might be a little bit intimidating to try that in a public setting. So I have this Jumbo Swap app, which is also very interesting in its own right. So I'll quickly go through how that works. Just quickly before I get into that. So once you have all of this stuff together, you've figured out how to make your circuit and you understand what's going on. In order to make this into an application, you use MPC framework for that. And this is like literally pretty much all of the API. So you just compile your circuit, you instantiate a protocol, you tell the protocol how to send and receive bytes and then you can just await the output. Simple as that. We also support all of the major JavaScript runtimes, and they interop with each other as well. So you can have one client on Firefox and another client on Dino or Bun, and they can totally do MPC with each other just fine. So I have these charm things here. So come up and grab one of those after this, if we have time, or if you're going to like pub with some people after this, feel free to grab one of these. Please grab one at random, because the whole point is we're going to be facilitating swaps. And if you pick your favorite one out of the bag, then that spoils the whole point. So just pick one at random, please. So Jumbo Swap allows you to do this very simple swapping idea where it's just like one for one item, and you can be in groups. Another key thing about this MPC stuff is it works not just between two people, but in theory between any number of participants. Please don't try too many with this app because it will break. So start with 5 or fewer and then maybe brave higher numbers. But so it solves, part of what it does, I think, is it solves this economic problem, which is when you want to trade with somebody, you're actually incentivized not to initiate the conversation, which is a terrible outcome. If everybody does the optimal thing, then nobody wants to talk to each other. The reason for that is, like, imagine if you had the ice cream and you want the cake. If you say that, the person with the cake is going to be like, oh, my cake must be really valuable. And like, you don't want your ice cream. So why would I want your ice cream? So this is terrible. And what Jumbo Swap allows you to do is everybody is incentivized to freely express their full preferences, because the only thing that will be revealed is the swaps that you actually get to make, because we calculate it with MPC naturally. So similar idea, this time one person hosts, and because we have more than 2 people, everybody else joins. And you just, yeah, everybody scans that QR code. Don't scan this one, it's a temporary thing. And everybody puts in their name and the thing that they want to swap for. And then you just indicate which things would you rather have than the thing that you currently have. You submit, it calculates, and then you get the results, and everybody finds out, you know, who they should give their thing to and what thing they should get from somebody else. And, you know, this is not enforced because, like I mentioned at the beginning of the talk, we're not talking about how to do this with blockchain. But, you know, in this kind of situation, you're all incentivized once this is revealed to actually go forward with the trade, because, you know, the app will only uncover something that's consistent with everybody's preferences. So once they're revealed, you can just be like, yeah, I actually want to do that. And so you can actually swap those items. And then everybody is really happy because they got a thing that's better than the thing that they had before. And that's the end of my talk. Thank you so much. Please come back next month to verify how MPC works. In the meantime, are there any questions? Well, we got a few.
All righty. You want to start us off? Actually using the catch box for its intended purpose. I like it. Is there a practical limit on how big a Boolean circuit you can generate from someone, right? Because is there like any sort of combinatorial explosion based on the logic that you've implemented in actual programming language and converting that into what is a very rudimentary Boolean circuit?
Totally, yeah. So you will run into limits if you try to push this thing. It's not very hard. You can totally do interesting things. For example, we've been performance testing with SHA-256, and you can do a SHA-256 in like a couple of seconds, which I think is pretty good. But yeah, you can easily design a program which does a lot more computation. And so, yeah, one of the things that I didn't cover in the talk is that the really interesting thing actually that Summon does is that you can have branches in your program, and it has to, because this is MPC and nobody gets to see what happens, the MPC actually has to calculate both sides and then fuse them together. And so this can generate a lot of stuff. And if you're not careful when you're writing your Summon code, you can easily define like an infinite circuit. If you just have like a loop that isn't definitely going to determinate because of like values that are in the clear, then it will just do that. I actually need to improve the error handling around that. But yeah, you can make like gigabytes worth of circuitry out of Summon. I have tested that, and so you can do a lot.
All right. Anyone else? Yep.
You mentioned branching. Can I run this on a GPU? Is that kind of the point of the same? Is it the same rules, right, as running like a GPU code, which can't branch or shouldn't branch?
No. So no, it's not like that. And no, unfortunately, we don't have any GPU optimizations so far. But to very quickly, so I have these bonus slides. So the point is that you can do branching, but it has to evaluate. I mean, I guess maybe this is the same kind of thing. Yeah, it has to evaluate both of them, and yeah, that's how we. Maybe it is similar to. I actually don't know much about GPU programming.
Hey, I'm completely new to this. What is circuits? What are circuits? Like, never heard of it.
So circuit, where's a good slide for that? Oh my gosh. So this slide. So you can see here, you have these nodes that connect to each other like this. That's what I mean by a circuit.
Okay. Yeah, just nodes that connect. And sometimes they're Boolean and sometimes they're algorithmic.
Totally, yeah.
Okay, arithmetic.
I think like the core feature actually of a circuit, because you can also represent it in different ways and it's not super obvious if you don't make a diagram. The core thing is actually kind of that branching thing, is that circuits can't branch. There's a fixed flow of execution that has to happen.
Thank you. Thank you.
Oh, wow, so many.
So what happens if everyone wants cake?
So in Jumbo Swap, if that happens, so it'll only identify swaps that are mutually consensual, I guess. And if it can't find any because everybody just wants the cake and nothing else, then the output will be, sorry, but no swaps were found that you could do.
Hi, what's the application of this for Ethereum?
Yeah, so I have a quick slide about this. So there are different like concrete ways to apply it. This very briefly is the underlying mechanism that I have in mind, where yeah, you can stake to make sure that you reveal things, and instead of calculating the output directly, you generate shares over the output. And so before you combine those shares, you commit to revealing what they will be, and then you combine them together, and then that can be executed on chain. So we have some use cases in mind. This is one of them. So for example, if you want to sell something, you might be interested in offering discounts for eligible customers. And so, but that's like personal data. And so you could offer discounts to people without them having to disclose exactly how they are eligible for that discount. And you could calculate that under MPC. Another one is auctions. So if you have an item you want to auction it off, and we could calculate this under MPC and link it to some settlement on chain, make it work that way.
I'm impressed you have so many bonus slides for these questions. I feel like we need to figure out what the questions are to get the stupid slides.
I've been working hard on these presentations, so I get to mix and match them from different ones.
Any more questions? I have one myself, actually. So you mentioned there's no magic computer in the middle that you have to trust, right? So it's, where does the computation happen? Is it on all parties' computers? But then every party has to do the whole calculation? How do you get the data to do part of the calculation? Like,
yeah, so it's complicated. Basically, at least in the vanilla case with two parties, it's relatively simple. It gets a bit more complicated with more than two. But with two parties, what happens is it kind of is just one person that's evaluating it, but they can't see what they're evaluating. And it'll make more sense next month when I explain how it works.
all right, I think that's it. Yeah.
All right.
That was amazing.
Thanks so much. Come and get your charm if you want to try Jumbo Swap. Do we have time is there socialization time after this, or are we running?
Yeah, I think so. We're only 8 o'clock. We've got till 9. So yeah, sure.
Awesome. If you want to try Jumbo Swap, come take a thing and I will show you the process, and yeah.
Thanks, Andrew. That was amazing. Can we please give Andrew one more round of applause?